There. So in this video, we're going to be taking a look at problem set 4.4, Oligopoly, number 2. Now, one thing to know is that I didn't put this inside of your packet because this is actually a practice problem that's coming directly from an AP exam. So what I'd like you to do, if you'd like to, is Google search 2019 AP Micro FRQ. And this should come up as a PDF. And this is the third question that students received that year. And I'd like us actually to try it as our practice problem in class. So I'll put that here, 2019. If you were to Google search this, Micro FRQ, it'll come up as a PDF, and you click down and you find the third problem. So this is a problem with a game theory, and it says Patrick's Pie is the only pizzeria in College Town it can choose to advertise or not. And then D's Pizzeria is contemplating whether to enter. And then each independently and simultaneously makes its decision, and that way it's like a one-shot deal. The payoff matrix shows their profits, and then both players have all the information. The first entries in the payoff matrix, the one on the left, are Patrick's profit, the one on the right are D's. And then A, it says what maximizes the total profits for Patrick's Pie and D's Pizzeria. So that one isn't terribly complex. It's just like look down there and see like where do they add up to be the biggest. And that's, for us, A would be Patrick advertise, and D stay out, right? And so you just kind of add the two numbers together and you'll see that that's 175. It's the biggest one. So B says, conditional on your response in A, does Patrick's Pie or D's Pizza have an incentive to cheat on this combination of actions that maximize the combined total profits? Explain using numbers from the matrix for each pizzeria. So for this one, we actually have to solve the problem. So I'm going to draw this payoff matrix over here on this side. And so we'll say in and out and advertise and not. And so that's D and that's Patrick. And so we have 50 and -2. We have 175 and 0, 150 and 15, and 100 and 0. So now we're just going to solve it, and then we'll see if they have an incentive to cheat. What that's really saying is like, are they going to be pulled farther away, right, from this, this point? In other words, is this point a Nash equilibrium is really what it's asking. So let's start if we're Patrick and we choose, and we think, we think D will come in. Should we get 50 or 150? Well, if we think D is coming into the market, we should not advertise and get 150. At the same time, if we think D is coming into the market, we can advertise and get 175, or we can not advertise and get 100. So we're going to advertise and get 175. So as Patrick, we don't have a dominant strategy. If we're D, on the other hand, and we think Patrick's going to advertise, what do? Do we jump in and lose 2, or do we stay out and get 0? Well, we stay out and get 0. On the other hand, if we're here, right, D and thinking that he's not going to advertise, if we jump in, we get 15. If we stay out, we get 0. So we'll jump in, right? So in this case, right, we think about conditional on our response in A, which would be that this is where we start. Do either one have an incentive to cheat on that combination? Explain using numbers. And so we'd say that the answer is no. No for Pat, because 175 is greater than, and for him, right, it's greater than 100. Because for him, he can choose to advertise or not, so he's going to stay there. And no for D, because for her, 0 is better than -2. 0 is greater than -2. Okay, so now it says C, does Patrick's Pie have a dominant strategy? And we can actually see very, very clearly that he does not. He might advertise if D stays out, and he might not advertise if D jumps in. So we would say, no, that's all we have to say. There's no explanation needed. D, identify the Nash or equilibrium or equilibria. And so we would say there are 2, and so we have to identify both. Pat, not advertise, and D in, and D enter. And so we have to identify both of them. And Patrick advertise plus D stays out. And so if we're either in this one or in this one. Then it says part E, ignoring antitrust considerations of a pizza market. Suppose that Patrick pays D's pizza if she chooses to stay out. Redraw the payoff matrix and see how her payment affects the payoffs. Identify the equilibrium for the redraw matrix. Okay, so we're going to redraw, right? And we'll just kind of see here in D, out, advertise, not, and Pat. So now, if D stays in, she gets the same amount. So we'd say -2 and 15. And Pat, for him, right, you know, if we're thinking about that, if we're paying him, we have to think about that we're actually reducing his profits if she stays out as well. But that means that it'll stay the same if she stays in, 150, right? So this column is going to be the same. This one's weird because, in fact, if she stays out, she's going to get 20, but he'll only get 155, right? And why is that? Well, because he's got to pay her. So he's paying her the 20. That's just moving basically 20 over. And then we go 80 and 20 here. So now we basically resolve this thing. And so we see like, okay, if Patrick thinks D is going to come in, he's going to not advertise still. And if he thinks that she's going to stay out, he'll still advertise. And for her, if she thinks that he's going to advertise, she could jump in and lose 2 or stay out and get 20. Or she could, if she thinks he's not going to advertise, she could jump in and get 15 or stay out and get 20. And so she'll do that. So now, right, she has a dominant strategy to stay out. And so we would basically say for E1, we did that. E2, identify the Nash equilibria, and that is just Pat, advertise, and D stays out. Oops, D stays out. So it's kind of an interesting problem. I hope that this helped you work through it, and I'll see you next time.